I now want to change to electromagnetic waves. Electromagnetic waves travel with the speed of light, which is 300,000 kilometers per second. And if you want to treat that correctly, you would have to use special relativity. In the case of sound, I stressed repeatedly that you in the audience should not move, but that the sound source is moving. In the case of electromagnetic radiation, when you deal with the speed of light, you don't have to ask that question. It is a meaningless question in special relativity to ask whether you are moving relative to me or whether I am moving relative to you. It doesn't matter. All that matters in special relativity is the relative motion. So you can always think of yourself as standing still and make the source of electromagnetic radiation move to you or away from you, relative to you. Electromagnetic radiation is optical light, infrared, ultraviolet, radio, X-rays, gamma rays. All of that is electromagnetic radiation. If the velocity of the source of electromagnetic radiation, the transmitter, if that is way, way smaller than the speed of light, then it is very easy to predict the change in frequency due to Doppler shift. Let this be the transmitter, which produces frequency f, and here is the receiver, which receives a frequency f prime. And let the velocity of the source of electromagnetic radiation be v. I could put transmitter here, but we can drop that index, and let this angle be theta. Then this is the component in u direction. We call that the radial component, which is v cosine theta. So I delete the tr. This is just the velocity of the source relative to u at that angle. If now we want to know what f prime is, then f prime equals f times 1 plus v over c times the cosine of theta. What matters is only the radial component of the velocity. This is the radial component. If theta is 90 degrees, just like we had with sound, then f prime equals f. For 90 degrees, the cosine of theta is 0, f prime equals f. If theta is smaller than 90 degrees, then it's coming towards you, then f prime equals larger than f. Theta equals larger than 90 degrees, it's going away from you, then f prime equals smaller than f. You would get a similar equation for sound by replacing this c by the speed of sound. But I want to stress that this only holds for electromagnetic radiation if v over c is much, much smaller than 1. Now, when we deal with sound, there is something mechanically oscillating. Something is vibrating. With electromagnetic radiation, charges are vibrating, electrons are vibrating. And they are vibrating with a certain frequency, and that means there is a certain period of one oscillation, and that period of one oscillation is, of course, 1 over the frequency. I can ask myself now the question, how far does electromagnetic radiation, how far does light travel in the time of one period, capital T? Well, it goes with the speed of light, so in capital T seconds, it moves a distance ct. And that distance we call the wavelength of electromagnetic radiation. Lambda equals ct, for which you can also write c divided by f. So this is the wavelength of the electromagnetic radiation, the speed of light, 300,000 kilometers per second, the period of one oscillation, say of the electrons, and this is the frequency which you can give in hertz. I could give you a specific example. I, for instance, can take a period t of 2 times 10 to the minus 15 seconds. That would give me a wavelength of about 6 times 10 to the minus 7 meters. 6 times 10 to the minus 7 meters, and that you would experience as red light. If I make the period shorter, say 1.3 times 10 to the minus 15 seconds, I get a shorter wavelength. I get 4 times 10 to the minus 7 meters, and you would experience that as blue light. In astronomy, in optical astronomy, we cannot measure the period or the frequency of optical light. All we can measure is the wavelength. And so if I want to use this equation, then I have to replace f prime by c divided by lambda prime, and f I have to replace by c divided by lambda. And when I do that, I get the following result. I get lambda prime equals lambda times 1 minus v over c cosine theta. If this is a plus, this is a minus. Check that for yourself. You have to use the Taylor expansion, namely that v over c is much, much smaller than 1. So you can see now, if the object comes to you, in other words, if f prime is larger than f, if the frequency is higher, then the wavelength will be smaller. And so let me write that down. When the cosine of theta, so the object is coming to you, the cosine of theta is larger than 0, the object is approaching you, then the wavelength lambda prime will be less than lambda, and that has a name. We call that blue shift. And the reason why we call that blue shift is that if the wavelengths become shorter, it moves towards the blue end of the spectrum, because blue has a lower wavelength than red. If cosine theta is negative, then the object is receding from you. Then lambda prime is larger than lambda, and we call that redshift. These are the terms that astronomers use all the time. When you make a spectrum of a star, you can do that using prisms or by other means, and you look at the light intensity as a function of wavelength. So here is the light intensity as a function of wavelength. Then you may expect to see some kind of a continuum, but in fact what you do see is superimposed on a continuum. You see sometimes very sharp absorption lines, black missing light, called absorption lines. And these absorption lines correspond to elements in the atmosphere of the star. In fact, if you see the absorption lines, you can tell what kind of elements are present in the star. Some are very characteristic absorption lines for hydrogen, some for calcium, some for silicon, some for magnesium, and so on. It's actually interesting that when you look at the spectrum of the sun, when people did that first, when they had the means of doing that, they found absorption lines in the spectrum of the sun which could not be identified. They had never been seen here on Earth, these lines, and so they called these lines after the sun. The sun is Helios, and so they called it helium. So helium was first discovered on the sun before it was later discovered on Earth, by looking at the absorption lines of the solar spectrum. If a star moves to you, then all the lines, every single line will be blue shifted, and if the star moves away from you, all the lines will be red shifted. If you take an example, if lambda prime divided by lambda, you pick any one of those lines, it doesn't matter which you pick, because they will all do exactly the same. If this were, for instance, 1.00333, I just pick a very nice number, that means lambda prime, as you see, is larger than lambda. The wavelengths get longer, so we have a redshift, and you substitute that in that equation, then you'll find that the velocity at which that star is moving relative to you, that gives you immediately the answer there, equals minus 0.00333 times the speed of light. c, and that is minus 100 kilometers per second. And the minus then reminds you that the object is receding from you. So that gives you a redshift. I just wrote down that the velocity v is minus 100 kilometers per second. It's of course v cosine theta that is minus 100 kilometers per second. It's the radial velocity. That's all you can measure. You have no information on theta. So it is this component, v cosine theta, which we call the radial velocity, that is minus 100 kilometers per second.